Assalamualaikum. Good day. Today, our group would like to present our case study for theory of structure. First of all, our case study takes place in Taman Sri Tualang of Bridge 41 from ECRL, one of ECRL's bridge here in Temerloh, which crossing the access road to Taman Sri Tualang. This bridge consists of 2 span and 3 support. Later, my friend will explain the ideas and the problem statement which leads to this case study. Thank you.
Assalamualaikum and hi everyone. Today I'll be talking about our case study on bridge settlement, focusing on Bridge 41, part of the ECRL project located in Taman Sri Tualang. This bridge has 2 spans. Span AB is 30 meters and span BC is 20 meters. Our goal is to analyze the structural behavior of the bridge with and without settlement, and to understand how settlement impacts its safety and performance. 3 months after the bridge completion, during the peak of the rainy seasons, cracks were observed on the bridge deck near the middle band. Measurement revealed that the band at axis B had settled by 18 centimeters and the abutment at axis A had settled by 3 centimeters. Our task was to investigate the cause of this settlement, analyze its effect, and determine whether the bridge is safe for continued operation. Our investigation process involved several key steps. First step, organizing the investigation team to identify the necessary expertise and develop a step-by-step procedure to carry out the investigation. Second step is developing failure hypothesis, and we formulated 2 possible hypotheses for the observed settlement and cracks. First hypothesis, settlement due to soil conditions and foundation instability. Second hypothesis, settlement caused by material deformation under external load. Step 3, structural analysis. We analyze the bridge using the moment distribution method to compare the bridge behavior with and without settlement. Step 4, decision on bridge integrity. Based on our analysis, we determine whether the bridge is safe for future operation or traffic should be halted for further rehabilitation. For structural analysis, we use moment distribution method to calculate the shear force and the bending moment in the bridge in 2 scenarios. First scenario is without settlement. The bridge was analyzed under normal condition with no settlement. And the second scenario is with settlement. The bridge was analyzed considering the 18 cm settlement at band B and 3 cm settlement at abutment A. We calculated the fixed end moment, stiffness factor, and distribution factor, and we distribute the moment to find the final moment in the structure. Our analysis reveals several key findings. First, without settlement, the bridge experienced predictable stress and deformation pattern due to external load. Second, with settlement, additional moment were induced, leading to increased stress and deformation. For example, the settlement at band B caused by significant increase in bending moment, which contribute to the crack observed on the bridge deck. Third, safety implication. The increased stress and deformation compromised the bridge structural integrity, raising concern about its long-term safety. Okay, that's all from me. Thank you.
Hello everyone, I would like to present the next step of the case study, and most important is calculation part. From my overview, as we know that the bridge have 2 span and 3 support. So the outcome from my group discussion, our team member have decided to put 1 point load and 1 uniform distribution load UDA on the bridge as we know as supporting beam. First of all, the span of member AB is 30 meter length and the point load located at center of span. Next span of member BC with 20 meter length and UDA is fully loading on this span. First step on this calculation is to find the distribution factor for every members. That means member AB, BC and CB. For support A is member AB, and for support B, we know that the span have two-way members, that is member BA and BC, and the last support is C, and we call that member CB. Then for this method, we need to using formula stiffness 4EI over L to get the value of distribution factor. Distribution factor is, or we call that is DF value, is the value from K value divided to sum of K value. For member AB, we get 1.0 value of distribution factor. Next, for the member BA, we get 0.4 and 0.6 for member BC, and the last member is CB, we get the value 1.0. Next step is fixed end moment calculation. As per general formula, for the point load, we need to use minus PL over 8, and P stand for loading value and L stand for line of span value. Different with UDL loading for span BC. This formula need to use minus WL over 12, and W stand for UDL loading and L stand for line of span. For moment fixed AB and BA, we get the answers is 75 kN and minus 75 kN. For fixed and moment BC and CB, we get the value is 666.67 kN. Then the next step is moment distribution table. On this table, we need to balance the member of BC. After two time balance, we get the sum of value of the total moment at the support. After we get the value of the moment, we need to calculate again to find the support reaction at every support. Then after we get the value, we can draw the shear force diagram and bending moment diagram. This process is repeating for the bridge with settlement, but the moment of settlement value is too small and EI is constant. The value from these two situations we find as same as well when EI is constant. The shape of SFD and BMD with these two situations also same. For the SFD and BMD review, we can explain the bridge has some value of settlement. That's all for me. I pass to my friend for the next part. Thank you.
Hi, Assalamualaikum. My name is Nabila. For my part, I'm going to tell about our case study conclusion. Bridges are a crucial part of modern infrastructure connecting communities and facilitating transportation. However, like any other structure, bridges experience settlement due to various factors, including material formation, soil conditions, and deterioration over time. Today, we will explore how bridge settlement occurs, its impact on structural integrity, and how engineers can mitigate its effect. Bridge settlement is caused by external load pressing down on the structure, leading to gradual shift and formation. This can result in an imbalance, increasing stress and deformation, which may ultimately compromise the safety and longevity of the bridge. By comparing the bridge with and without settlement, we can observe the significant changes in load distribution, foundation stability, and overall performance. Engineers use numerical modeling and structural analysis to predict and understand this effect. Through advanced engineering techniques, we can identify potential risks early and develop effective mitigation strategies. These approaches help reduce imbalance and extend the service life of bridges, ensuring their long-term functionality. Understanding the factors and contribute to bridge settlement allow engineers to design safer and more durable structures, which through analysis and proper maintenance, we can enhance the stability of bridges and improve public safety. As we continue to advance in engineering and technologies, and addressing bridge settlement remains a priority. By implementing strategic solutions, we can ensure that our bridges remain strong, resilient, and safe for generations to come. Thank you for watching.